Good day. Today's topic is all about the confusion matrix. But let's take a look at our data. We have here sample data sets on breast cancer, and we would like to analyze this by applying classification algorithm. And the classifier will be giving us this output. The aim of the classifier is to identify whether there are recurrence in breast cancer patients or none. So the first part is the classifier use, which is stated in here. We have the naive Bayes classifier. The data set is the breast cancer. We also have here the breast cancer data set. And then the number of instances is displayed in here. And then we also have the 10 attributes, which started with age up to class. And then the test mode used, which is the tenfold cross-validation, which was used to validate the model. So we have here. And then also, next part is the classifier model full training set, which displays the performance of the naive Bayes classifier in each of the following attribute cases. And then we also have here the classifier output. The classifier output also displays the stratified cross-validation summary on the evaluation of the performance of the classifier. So to better understand what was being displayed, we better have a clear understanding about the confusion matrix. We have here the confusion matrix at the bottom. And the TP rate, we have the TP rate here, and then the FP rate here. The precision, the recall, and the F measure are also known as the F1 score. So first, let's define what is a confusion matrix. Confusion matrix is a table used to evaluate the performance of a classification model by comparing the actual labels of the predicted labels and the actual labels. It is also known as an error matrix. Confusion matrix also provides a comprehensive view of how well the model is performing and where it may be making errors. It provides insight into the performance of a classification algorithm. So we have here the structure of the confusion matrix. So what you can see is a 2 by 2 matrix for binary classification problems, but it can also be extended into a larger matrices for a multi-class problems. So the basic structure is this one, and then the components of a 2 by 2 confusion matrix is we have the true positive here. The true positive is the number of correctly predicted positive cases. We also have here our true negative. The true negative is the number of correctly predicted negative cases. We also have here the false positive. False positive is the number of cases where the model correctly predicted a positive class, also known as a type 1 error. And then the last part, we have here our false negative. False negative is the number of cases where the model incorrectly predicted a negative class. It is also known as our type 2 error. Put this one into an example. So we have here a given example. So suppose a model is used to predict whether a person has a disease, positive or not, negative, based on some medical data. So there are 165 sample data. So after making the predictions, the confusion matrix looks like this. So we have here our predicted positive, our predicted negative, our actual positive, and our actual negative. So let's interpret the content of our confusion matrix. So there are 165 total number of samples. So we are just going to add the true positive value, the false positive, the false negative, and the true negative. So our N is equivalent to 165. And then the model correctly predicted 50 as having the disease. So we have here our true positive, which is 50 as having the disease. And then the model missed 10 people who actually have the disease. So we have here. So the model predicted it to be negative, but in reality, or the actual data says it is actual positive. It has a disease. And then the model incorrectly identified 5 people as having a disease. So we have here, when the model runs, it predicted that there are 5 people who have the disease, but in reality, they don't have the disease. And lastly, the model correctly identified 100 people as not having the disease. So it means that when the model runs, it identified or it classified 100 patients who do not have the disease. And it is true that they do not have the disease because the predicted negative is actual negative. So these are the different metrics derived from the confusion matrix. So usually, we start with the accuracy in order for us to identify the performance of the model. So the accuracy is the proportion of correct predictions, both positive and negative, out of all the predictions made by the model. So from the confusion matrix, several performance metrics can be evaluated, and one of them is the accuracy. These metrics help to evaluate and compare the performance of a classification model in a more detailed manner. So the accuracy is equal to the true positive, or the sum of true positive plus true negative we have here, divided by the total number of instances, or our n. And next metrics is we have our precision. Precision is the proportion of correctly predicted positive cases out of all the cases predicted as positive. So high precision indicates an example labeled as positive is indeed positive. It signifies that we have a small number of false positives. So the formula for that is precision is equal to true positive divided by the sum of the true positive and the false negative. We have our recall. Recall is also known as sensitivity or true positive rate. Recall is the proportion of actual positive cases. So we have here the actual positive cases that the model correctly identified. So the formula used for recall is recall divided by the true positive rate divided by the sum of the true positive plus the false negative. Metrics used is the specificity or the true negative rate. The true negative rate is the proportion of the actual negative cases. So we have here our true negative cases that the model correctly identified. So the formula is true negative divided by the sum of the true negative and the false positive. And lastly, we have the or the so-called F1 score. It is the harmonic mean of precision and recall, providing a balance between the two. So our formula would be F1 score is equal to 2 times the product of precision times recall divided by the sum of precision plus recall. So let's evaluate, or let's put this in example. So we have here a given example. Suppose a model is used to predict whether a person has a disease or not. So we are just going back to our first example a while ago. So there are about 165 samples. After making predictions, your confusion matrix looks like this. So this is where we are going to derive, or we are going to evaluate this confusion matrix by this one. So first, let's interpret our table. So we have 50 true positive, we have 5 false positive, 10 false negative, and we also have 100 true negative. Then how to analyze the confusion matrix? We can analyze this one by using the key metrics we have discussed a while ago. So we have here the accuracy. So substituting now the values of TP, which is 50, plus TN, which is 100, divided by the total number of our instances. So we have here the different instances. We have the true positive, the true negative, the false positive, and we have the false negative. And then we will get 90.91, which means that the model is highly accurate with around 90.91% of all the predictions being correct. Now for precision, so we have here the formula for precision. True positive divided by true positive plus false positive. Now let's substitute the values. The value for true positive is 50 divided by true positive plus false positive, which is 5. So we have 50 divided by 55. We have approximately 90.91%. It means that the model's precision is high, meaning that when it predicts someone has the disease, it is correct around 90.91% of the time. And the next, we have here our recall. Substituting the values, so we have 50, our TP, divided by the sum of 50 plus 10, we will be having approximately 83.33%. This means that the recall is relatively high, indicating that the model captures 83.33% of people who have the disease. And on the other hand, we have the specificity, the true negative divided by the sum of true negative and the false positive. Substituting the values, we have true negative 100, and false positive 5. So we have 100 divided by 105, we will get approximately 95.24%. So this means that the model correctly identifies 95.24% of people who do not have the disease, which shows a good performance in avoiding false positives. And lastly, we have the F1 score. So substituting now the values, so you will get the decimal numbers instead of the percentage for this one. So we have here our precision, our recall, precision, and recall. And then we will get approximately 86 or 0.8696, so around 87%. So this means that the F1 score of around 87% suggests a good balance between our precision and recall. Overall analysis is that high accuracy of 90.91%, meaning it makes correct predictions most of the time. The model also has a high precision of 90.91%, which is crucial when false positive needs to be minimized, such as when misclassifying a healthy person as diseased could lead to unnecessary anxiety or treatment. On the other hand, good recall of 83.33% suggests that the model identifies most actual disease cases, though it does miss some. High specificity of 95.24%, indicating that the model accurately classifies people without disease. So overall, the slight trade-off between recall and precision is seen where the model might miss a few actual positive cases, which is our false negative, but it has a low rate of falsely predicting the disease in healthy individuals. That is our false positive. Thus, this model could be suitable in scenarios where precision and avoiding false positive are prioritized, such as in initial disease screening tests. We have here sample problems. So as a classifier made a total of 150 predictions, so we have here our N to be 150. Then out of 150 cases, the classifier predicted yes. So we have here 100 times. This is our positive. And then predicted no 50 times. So since in our confusion matrix, there are no exact data for yes, positive, or no, negative. So let's just assume the given values for the meantime. So the total predictions is 150. So we have N here as 150. And then the predicted yes is 100. So we have here, the total here is 100. It means that when you add the TP and the FP, it is equivalent to 100. So we have here 80. This is an assigned value for our TP. We have 30 here, assigned value for our TN. And then we have our FP. And also we have our F. And here, take note that these values are just assigned values or assumed values. And then we also have 50 here to be our predicted negative or predicted no. Next example is we are presented with raw data. So we have here the expected and the predicted. We have your expected and then the predicted. Expected data falls on the first column we have here, and predicted falls on our second column. So let's turn our results, this one. We have here the result into a confusion matrix. So first we must calculate the number of correct predictions for each classes. So we have here, the algorithm made 7 out of 10 predictions correct with an accuracy of 70. So our first given is we have n, our sample or instances, which is equivalent to 10 predictions. And then we also have now our accuracy, which is equivalent to 70%. And now we are going to write our confusion matrix. So we have here our given uh, raw data, and this one is our confusion matrix. So let's evaluate our confusion matrix. So here, we have here our predicted column, and we focus on the predicted column first. And we have here the predicted men. This one is our predicted men, and this one is our predicted women. And then we have here the actual men, and we also have here our actual women. So it says that there are 7 correct predictions. So 7 correct predictions, therefore we have here our true positive 3, we have true negative here, which is 4, which is equivalent to 7. And we have 10 predictions. So adding now 7 plus the remaining 2 predictions, we have our false positive 1 plus our false negative, which is 2. This is now equivalent to 10 predictions. So we have already here 10, this one. So our value for n, our number of instances is 10. Now let's try to check whether these 3 values for true positive is correct. So it says here that the algorithm or the model predicted 3 men as men. So we can try to look at our raw data here. So we have here men, this one, as man. We also have row 5, man as man. Here, man as man. And yeah, so we have 1, 2, and 3. So therefore, our true positive is 3. And let's try to check here if there are really 4 women predicted as women. So the expected is, we have here woman, that is number 1. We have also here woman as woman, another woman as woman, and we have here another woman as woman. So we have 4 true negative. So predicted as women, and they are actually women. And then we have here false positive. They are predicted to be men, but they are actually women. So we have here, let's try to look at this. So woman, but predicted to be men. So we have only one. Yes, so we have only one here. So therefore our true positive or false positive is correct. And then we have predicted as men, but they are actually men. Or no, predicted as women, I should say, but they are actually men. So we have here, let's try to look at that one. So actual or expected is man, and predicted as women. So we have number 1. And we have here another one. Predicted as or expected as men, but they are predicted as women. So we have 1, this one, and 2. So therefore, we have false negative as 2. So that is how we are going to plot or make or create our confusion matrix. So these are the list of rates that are often computed in a confusion matrix of a binary classifier. So first is we have the accuracy, which was mentioned a while ago. We also have our misclassification rate. The formula is false positive plus false negative divided by the total number of samples. Or we could get our accuracy 100 minus our accuracy, then we will be having the misclassification rate or the error rate. The true positive rate, when it actually yes, how often does it predict yes? And false positive rate, recall or sensitivity, when it is actually no, how often does the model predict it as yes? And then we have here our true negative or the specificity or precision. We also have the prevalence. Other terms you can find in the output of a classifier is the null error rate. This is how often you would be wrong if you always predicted the majority class. And then we also have the Cohen's kappa. This is essential measure of how well the classifier performed as compared to how it would have performed by chance. In other words, the model will have a high kappa score if there is a big difference between the accuracy and the null error. The ROC curve, this is commonly used graph to summarize the performance of a classifier over all possible thresholds. So it is generated by plotting the true positive rate, which would be the y-axis, and then the false positive rate, which would be the x-axis as you vary from the threshold for assigning observations to a given class. Now let's take a look at our next problem. So suppose a machine learning model is developed to classify emails as spam or not spam. And after testing the model, it was found out that there are 90 emails predicted as spam, but 20 emails are actually not a spam. And there are also 100 emails predicted as not a spam, but 10 of them are actually a spam. What we are going to do now is to write our confusion matrix. So we have here our confusion matrix. We have the predicted spam. We have here the predicted not spam. And then we have our actual spam and actual not spam. Now, the first thing that we are going to do is identify our n. So first, we are going to identify the value of n. So we have here first the total number of predicted spam. We have here 90. So we have 90 here plus the total number of predicted as not spam, which is 110. So all in all, we have 200. So our n is 200. And then let's place the true positive, the true negative, the false positive, and then the false negative. And the next to do is we are going now to identify our values for the true positive, true negative, false positive, and false negative. So let's evaluate. Let's try to look at our first sentence. So we have here, there are 90 emails predicted as spam. So it means that when you add the true positive value and then the false positive value, this one, we will get the total of 90 predicted as spam. Then we have here 110 emails predicted as not spam. It means when we add Fn plus Tn, we will get 110 not spam emails. So we have here. So 110 plus 90 is equivalent to our n, which is 200. The next, we are now going to plot this one. We have here the 20 mails that are actually not a spam. So it was predicted as a spam, but it is actually not a spam. So it is our false negative or false positive. And then we have here 10 that are predicted to be spam, but they are not actually a spam. So we have here our false negative. Now, as you look at our given problem, there's no value for the predicted spam and the predicted not spam. So what we are going to do is we just subtract 20, our FP, to our total spam to get our true positive. So 90 less 20, we will get 70 as our or as the value of our true positive. And then same through with the predicted not spam. So let's subtract 10 here from here. So we will get the value of 100. So if we try to add all the values in our confusion matrix, we have 70 plus 20 is 90, 10 plus 100 is 110, 110 plus 90 is equivalent to 200. Same through with this one. If you're going to add this, 70 plus 10, we have 80. And then we have 20 plus 100, we have 120. If we are going to add this one, we will also get 200, which is equivalent to our n. So if we are going to analyze now our confusion matrix, so the model correctly identified 70 email we have here. And then the model missed 10 spam emails, labeling them as not spam. So we have here. We also have the model incorrectly classified 20 not spam as spam emails, and the model correctly identified 100 emails as not a spam. Then now let's evaluate the performance of the model using our evaluation metrics. So we have here first is our accuracy, we have the precision, the recall, specificity, the F1 score. So applying now the formula for the accuracy. So we have here the true positive rate, the true negative rate, divided by the total number of samples. So we have them. So we will get 85%. So it means that the model correctly classified 85% of the emails, indicating reasonably good overall performance. And then applying the formula for precision, so we have here the true positive divided by the sum of true positive and false negative. We will get these decimal places 0.7778, or in percentage we have 77.78%. It means that when the model predicts an email as spam, it is correct about 77.78% of the time. This shows the model has a moderate false positive rate as of 22.22% of the predicted spam emails are not actually spam. So in recall, when we substitute the values for this one, we will get 87.5%. So the model successfully identified 87.5% of all the spam emails, indicating that it misses a relatively small number of spam emails. So that is 10 out of 80, or 10 out of 100. The model correctly classified 83.33% in terms of specificity of not spam emails, but it incorrectly labels 16.67% of non-spam emails as spam, which might lead to some inconvenience for users due to false positive. And then lastly, applying now the formula for our F1 score. So we will get 82.35%. This indicates a good balance between correctly identifying spam, our recall, and ensuring that most predicted spam emails are actually spam. That is our precision. So overall, the model performs well with an overall accuracy of 85%. And the model has a good recall of 87.5%, meaning it captures most of the actual spam emails. And then the precision of 77.78% is somewhat lower indicating that around 22.22% of the predicted spam emails are false positive. So this may suggest that the model is slightly aggressive in labeling emails as spam, which might result in some important not spam emails being filtered out. So let's go back to our previous example as shown in the first part of our presentation, which is the dataset breast cancer loaded in our Weka application. So we have here the result or the output of the classifier, wherein the breast cancer dataset are uploaded in a Weka application and the naive-Bayes classifier was applied with a 10-fold cross-validation. So the output is presented on the screen, this one. So this is our output, this one. This is the overall output of our classifier. So since we already know how to write and interpret a confusion matrix, and we already know what does accuracy, this one is our accuracy. What does the precision, this one, the recall, here. F1 score, here, means in the classifier output, we can now interpret the output of the naive-Bayes classifier to the breast cancer datasets. So let's start the interpretation. So let's start with this one, the accuracy. So we have here the accuracy, this one, the 71.6783%. So out of the 286 total instances, so we have here our total instances, we have 286. 205 were correctly classified. So we have here our correctly classified instances, which is 205, giving an accuracy of 71.68%. This indicates that 71.68% of the predictions made by the model match the true class labels. And next is the 28.32% we have here. This is our incorrectly classified instances. So what does this mean? It means that there are 81 instances. We have here our 81 instances were incorrectly classified, resulting in an error rate of 28.32. So this represents the percentage of instances where the model's predictions did not match the true class labels. And then we also have the kappa. You can see the kappa statistics here. We have here our kappa statistics, which is equivalent to 0.2857. So what does this mean? The kappa statistic is a measure of agreement between the predicted and the true class labels, taking into account the possibility of agreement by chance. So a kappa of 0.2857 suggests a low to moderate level of agreement beyond chance. And then next to this one, we also have our MAE, or the mean absolute error, which is equivalent to 0.3272. And we also have here the RMSE, or the root mean square error, which is equivalent to 4 or 0.4534. This error matrix measures the average prediction error. The mean absolute error, or the MAE, indicates the average magnitude of errors, while the root mean squared errors, or the RMSE, gives more weight to larger errors. So lower values indicate better accuracy, though both MAE and RMSE values indicate some error in the model. Then we also have the TP rate. We have here our TP rate. So the TP rate for the no recurrence events. So we have here the row for no recurrence events. This one. For the no recurrence events class, the model correctly classified 83.6 we have here. So 0.83 is equivalent to 83.6% of true positive instances. For recurrence events, we have 43.5 because we have here 0.435. So convert it into percentage, we have 43.5%. For the recurrence events class, the model correctly classified only 43.5% of the true positive instances. So the TP rate, also known as sensitivity or recall, is a measure of the model's ability to correctly identify positive instances of each class. Next, we go to our FP rate. We have here our FP rate. So now, no recurrence event is measured as 0.565 for no recurrence event. So therefore, we have 56.5%. And then we also have here our recurrence event, which is equivalent to 0.164, or we have 16.4%. So a lower FP rate is generally preferred as it indicates fewer incorrect classifications of negative. So for our precision, next we have our precision. We have here our precision. The no recurrence event, we have here the 77.8%, meaning that when the model predicted no recurrence event, it was correct 77.8% of the time. And when it predicted recurrence event, it has 52.9%, indicating a lower certainty its predictions for this class. And then for recall, we also have our recall here beside the precision we have here. This metric is the same as the TP rate and measures the model's ability to identify all actual positive instances for each class. And then we also have the F measure beside our recall. We have here our F measure or the F1 score. For the no recurrence event, we have 80.6%. This one. This means this is the harmonic mean of precision and recall, combining both measures into a single metric for each class. And then we have here the 0.477. A lower F measure for the recurrence events class indicates weaker performance for this class compared to no recurrence events. And then below this one, we also have our confusion matrix now. So this one, we have our confusion matrix. So we have here the classified. We have A and B to be the classified or the predicted. And then we have the actual, A and B. We have the recurrence and no recurrence events. So to interpret our matrix, we have 168 instances were correctly classified as no recurrence events. So we have, and then we have 33, we have here, 33 instances of no recurrence events were misclassified as recurrence events. And then next we have 48 instances, we have here, were correctly classified as recurrence events. And then we have 37 here, instances of recurrence events were misclassified as no recurrence events. So the confusion matrix provides a breakdown of how each class was classified, highlighting the model's strengths and weaknesses. In identifying each class, the higher number of correct classifications for no recurrence events suggests that the model performs better for this class than for recurrence events. The model shows better performance in identifying no recurrence events but struggles with recurrence events, as reflected in the low recall, precision, and F measure for the class. The relatively high error rate and the kappa or the low kappa statistics indicate that there is a room for improvement in the model's predictive accuracy.